In the previous parts, I made an introduction to what RNNs were, recurrent neural networks were, and we've talked about the reasons that people needed to step up to another architecture called LSTM, which was the difficulty of training the recurrent neural networks. And we were gently starting to introduce the idea of an LSTM. And what we've done was we've covered the basic architecture of it. And in this nice figure this guy put, we had seen the internal architecture very simply. So the things to note were, unlike the RNN, which had a single state vector, this guy had two separate state vectors, one being called the self state, the other being called the hidden state. Since we already know that RNNs were not capable of training for very long sequences, they had difficulty in learning long sequences, we could call them as recurrent neural networks which has short memories, because if I construct a long sequence, like a long sentence, the RNN is having difficulty to learn it. It is having difficulty to understand long-term memory sentences, which requires long-term memory. It is like you speak a long sentence and it says, I forgot what you said in the beginning of the sentence. This is like a short memory ability. That's why we resemble the hidden state that is used for the short-term memory of LSTM to the actual hidden state of RNN. So it was like RNN had only the short-term capabilities. LSTM had this both short and long-term capabilities. So how come these guys could create a model with long-term capabilities? Actually, self state being designed such like this in this architecture has a clear reason to provide long-term memory ability. However, we're not going to get into the details of why mathematically it is that way. What we're going to do is we're going to make a simple analysis on the architecture. We'll try to understand what this architecture is for. And hopefully, when you use this architecture feature in your codes, you will easily make a sense out of it. Because how you're going to use this architecture in your codes will be, you're going to be downloading, you're going to be borrowing it from a library like PyTorch or I don't know, TensorFlow, doesn't matter. It will be a function for you. So it will be a function with an interface. Okay, that's okay, no problems with that. But what you're going to do is you're going to use that function with some arguments and input and output arguments and with some properties. If you understand the internal dynamics, you will easily control that architecture. So that's what we are aiming for right now. So let us continue. So in addition to the hidden states, we have a concept of self states. Hidden states of an LSTM are pretty much similar to the hidden states of an RNN. Self states are related to the gates of the LSTM. From now on, I'm going to call these red sigmoid function parts as gates. Why do I call it gates? Because actually in the original design, Schmidt-Huber has prepared, these are just like logic gates of a logic circuit. I mean, what is a logic circuit? If you're coming from computer engineering and electrical engineering background, you know what a logic circuit is. A logic circuit is a circuit of AND gates, NAND gates, NOT gates, which is actually a mathematical circuit of zeros and ones. That's how the computers work. And remember, sigmoid gate, sigmoid function outputs values bounded between 0 and 1. So this is like a fuzzy gate, because there's a field called fuzzy logic in which you don't use binary values in that logic circuit, only zeros and ones, but you use values between zeros and ones as well. Those are called fuzzy logic circuits. So it is like sigmoid is providing zeros and ones and values between zeros and ones, because the output of a sigmoid would provide us values between zeros and ones, right? Fuzzy logic gates. And these gates in grayscale open and close they don't do it binary, 0 or 1, just totally closed or totally open, no. They barely close and barely open to let some things pass and to let some things not to pass, okay, to stop some things that are trying to pass. That's why, because of this nature of the sigmoid function, providing values between 0 and 1, just like a fuzzy logic gate, these will be called the gates. And just like it is stated in this sentence, the cell states of an LSTM are generated and designed according to the values of these so-called gates. Another important concept introduced to you, so you may feel a bit, I don't know, inconfident about it, but don't worry, we're going to get there. And we're going to talk about it soon in more detail. So the cell state continues from this path, okay? As it continues, it is either multiplied or, accumulated with some values coming from these gates. So cell state is maybe deleted totally because this is multiplication and the sigmoid gate can have 0 values, can be forgotten if it is multiplied by 0 here. If it is multiplied by all ones here, can be let go. It can be updated here. And in addition, as a result of these two operations, the new cell gate is constructed. That's why this state is called a long-term memory. It is either forgotten or being updated. So it's being accumulated over the events of the previous states. However, the hidden state A, which is the short-term memory, is going through so many operations before it creates the new one. That's why it is more likely to change, just like the short-term memory of your mind. Okay, another introduction. That's why self states are the long-term memory of an LSTM. Hidden states, the short-term memory, also called in cognitive science the working memory, is this way. So the short-term memory both exist in LSTM and vanilla RNN, but self state, the long-term memory, is something new for us. That's the ability of the LSTM to keep up well with these long sequences and long-term dependencies. So the gates of the LSTM is to create a cell state which can learn what information is relevant to keep forgetting or updating by these gates. How do these gates work? Before we get to that, let's remember how sigmoid and 10H work. Actually, we've talked about this today, but let's go over it on the slides as well. 10H is a function that creates values between -1 and +1. And sigmoid, the red ones, is a type of activation function which creates values between 0 and 1. They are bounded between these two values. So sigmoid sequentious values between 0 and 1. This is helpful to update or forget the incoming cell states when we need to. So that's why it is like a fuzzy logic gate. On the other hand, the 10H is kind of a creating new values between -1 and +1. So it is like creating an output for us. We'll get there. So to understand the dynamics and the architecture, I'm going to go over each architectural piece one by one. Actually, there are 4 important parts in the architecture. This part, the first part, which is the forget gate, which we are going to be talking about in a second. Then the input gate, then the output gate, and this is the cell state highway. It is where the cell state flows. It is like a highway. So you don't get stuck in the traffic. You can drive fast here. It's like a highway, if you can. So let's see what forget gate is. So in the forget gate, guys, in the forget gate, what happens is, let me get my pen. The input comes from here, sorry. The input comes from here, right? And the previous short-term memory, the hidden state, comes from here. And they get concatenated in a single vector, okay? And they enter this so-called gate. each node is like a perceptron. And inside a perceptron, as you will remember in neural networks, if something is a node, if it's a sort of perceptron, what you have inside is some weights multiplied by the input, which is a concatenated version of the hidden state and X, plus some bias, where the total sum is applied to an actuation function, which is a sigmoid in our case. This is the sigma letter indicating a sigmoid. It's very nice handwritten language. So what I have here is, I have a matrix of L by K plus 1, because the concatenation of X and N will create a vector of N plus K here to me. So this is N plus K times 1, a vector of N plus K length. Makes sense, right? I multiply it with a L times K plus 1 matrix and sum it with some B times L plus 1, because L is the length of the cell state. Cell state length, if you see, this is CL. The length of this guy is L. So at this point, I have a vector of length L. And the previous hidden cell state is also of length L. What I do is, I do an element-wise multiplication. This is also called the Hadamard multiplication in mathematics, if you remember from your calculus courses. So what you do is, at the end of this gate, the forget gate, you have a vector of values between 0 and 1, right? Because this is a sigmoid function. So inside you have a vector of length L, and each element of the vector is applied to a sigmoid function. So the output here will be some values between 0 and 1. 0, 0.1, 0.9, 0.2, 1, doesn't matter. And what you do here is, you element-wise multiply them with the cell state. So C1, C2 to CL for the first time instant, of course, if this is the first time instant. So you multiply them element-wise. So if there is a 0 at the first element of the output here, this element of the cell state will be forgotten. So it is like, at this gate, you are deciding, since this operation is multiplication, and since you are multiplying values between 0 and 1, you are trying to decide what parts of the cell state to forget, what parts of the cell state to keep, and since this is a fuzzy logic gate, what parts to keep some of them, and what parts to keep how much of them, because this is a value between 0 and 1. So if it is 0.5, you are like forgetting half of it. That's why this is called the forget gate, because there's a multiplication with an element-wise multiplication with a vector of the same length with values between 0 and 1. So you're forgetting some part of the cell state that you choose to forget, or you're not forgetting it. That's the beauty of the LSTM. So this is the forget gate. You may easily ask, how come these weights know what to forget, what not to forget, what to keep? Well, that's the beauty of neural networks, guys. We don't know. We just construct this architecture. Since this is a computational graph, we train it using backpropagation. With correct data and with correct ground truth, the weights are trained such that it serves that perfect purpose. So in my opinion, if you look at the advancements in the artificial intelligence field, deep learning-based artificial intelligence field, it is all about designing the correct architecture that would be easily trained, or finding a type of architecture which would be easy to train with, because you can find a very nice architecture, but if you are not able to train it, it's useless, right? So at the end of this part, this place, you have an updated intermediate cell state, which I call CCAP, where some of the elements of the previous cell state are forgotten, and some of them are kept, And there could be gray level forgetting as well. Some of the elements are partially forgotten, kind of. Good. I think it's okay. Please do not hesitate to interrupt me. Then we come to the second part, where we have the input gate. In this input gate, we have two nodes. The first node, this one, being a sigmoid function, again a gate, because it's going to be multiplied. The second one being a tangent function, tangent, hyperbolic tangent function. The aim of this gate is to find what parts of the input to add to this cell state. So if you observe carefully, the functions we have here is, for example, let me get my pen again. So same concatenated vector comes to here and here, which is this vector. So it enters this perceptron. It's a node. Inside we have some other weights. So the weights of this node, this node, this node, and all 5 nodes are different. It enters this node. And you obtain a value. Since this is sigmoid, again, the vector here is of length L, which is, because the hidden state vector, the cell state vector is L, which is values between 0s and 1s. So this is, again, a fuzzy gate, like a logic gate. The other branch that comes to here is still the same concatenated vector. It enters this perceptron, where there's a separate, different weight, different bias. Calculate this, and you feed it 10H, because this is blue. And here we have some values between -1 and +1. This is tangent, because these are values. These are the effect of the previous hidden state and the input. And with this multiplication here, you have this value here. So this vector is this, and this output is this. You again do an element-wise multiplication. Okay, let me do an element-wise multiplication. When you do this element-wise multiplication, here it is, as you can see, the sigmoid, the element-wise multiplication. You obtain, so it is here. You obtain here an input, an X, which is transformed with this 10H, and some parts of them are selected to continue, because this is a fuzzy logic gate. And I add it. So at this point, with the input gate, I decide what parts of the cell state to update with the incoming information that is related to the current input. That's why it's called the input gate. It's also called the update gate as well, because here we update the cell state according to the input. But originally, Schmidt-Huber calls it the input gate. Okay? This was the second part. As you can see, what we've done here was, first, we've decided which parts of the cell state to forget. Then, we've decided which parts of the cell state to update according to the incoming information from the input. And we are ready with the new cell state after these two gates. The final output gate is used to determine the new short-term memory. Okay, let's continue. And at this state, I have the new cell state because it continues. There's nothing stopping it. This is the new cell state. Okay, this is the update. So in the end, as an addition, as a result of the forget and input gates, we have the cell states. Okay, so the formulations and their names, ICAP, here ICAP, they're all explained. So at this is how you get the next cell state. This is CCAP, which you obtained after the forget gate, and this is the intermediate cell states being element-wise multiplied by this gate here and being added to here. This is the addition here, and you obtain the next cell state. And we have a final gate, guys, which is the output gate. We already have the cell state, new cell state. For this gate, we use the cell state, new cell state. Sorry. We use the new cell state here. It just enters, we have the new cell state. And we also have this concatenation of X and A being fed to here. So here. So this node, and we obtain this. At this point, we have this or this. And we have the cell state being fed to a 10H. As you can see, this is the new cell state, some weights that belongs to this perceptron. And at the end, here we have an element-wise multiplication. So we decide on the short-term memory state, the hidden state, the working memory state, as a result of the input, the previous hidden state, and the cell state. And you are good to go. As you can see, the working memory is affected from everything and is working very fast. It's changing very fast. But the long-term memory is designed to change in certain conditions. If something is to be forgotten, or is something to be updated. With this design, they were able to train many good models. Actually, LSTM changed everything, guys. And most of the models of Google and Amazon for search are using transformers today, but there are still valid models, I mean, used models today for LSTM. For example, when you type something on your Google search box, it is, I mean, completed according to you. I mean, if you write something, the next word will be different when I type something in my account, because there's a LSTM with weights specific for our searches individually that they use. So how am I going to use it for NLP and etc.? We are going to come there. Before, let's do some observations and let's try to understand the real job of the LSTM. So during the backpropagation, so this is like a computational graph, right? This architectural view is like a computational graph so that I can easily understand it. So because if this is a computational graph, the backpropagation will run in this direction, right? So there will be some sort of, this is a computational graph, the loss of the partial derivative of the loss of cell state T1 will be backpropagated in this direction, and the partial derivative of the loss with respect to A T1, whatever it is, will be backpropagated in this direction. So when you're backpropagating here, actually, since this is multiplication, it is addition, it will be rooted directly. And since this is multiplication, depending on the values of these guys, because in multiplication, it's rooted, yeah, I mean, the derivative will be the values of these parts. The values which are non-zeros will be backpropagating the gradient. So it is like you have a highway for the backpropagation. Actually, this is how they mathematically solve the vanishing gradients problem. They call this the highway, and in this highway, you don't lose any information. It is being run backwards and backwards. So during backprop, there is an open highway for the cell state. That's why we say cell state can learn long-term dependencies. During backprop, the hidden state is no different than a hidden state of the vanilla RNN. There's traffic congestion here. That's why it's prone to vanilla RNN problems like vanishing gradients. It is short-term memory. It won't be able to remember long-term dependencies. So in an LSTM, long is the cell state and short is the hidden state, term memory. Okay, you can think of this as the highway. After LSTM, we had another model. I call it the Chinese version, GRU, which is the gate recurrent unit, which is a simpler version of the LSTM. And this guy, Michael Fay, has drawn its figure in the same, using the same convention. So if it is LSTM, this is GRU. If you compare, LSTM has 5 perceptrons in it. This guy has 3 perceptrons, less weights and biases. LSTM has a separate short and long-term memory states. And for short-term memory, it has this state. For long-term memory, it has this state. So Schmidt-Huber, when they first designed it, they try to make the design separate such that they don't have to worry about what is short and what is long. In GRU, we had a single set of memory, which is going through the highway. Also, it is going through the short-term memory span. So it is like these are fused together in a single state. So in the hidden state of the GRU, some elements correspond to long-term memory, some elements correspond to short-term memory. I mean, fusing them or having this non-transparent concatenation of long or short-term states is not a problem for us because we don't want to understand what are short-term or what are long-term. We just want them to work. So if it's an efficient design and if it's easier to train, then it's good. And today is still a discussion. I mean, in the other course, sequence modeling course, we carry out a discussion in the lectures if LSTM is better or GRU is better, or if any other variant of LSTM can be better. But apparently, GRU and LSTM are the winners, and for some cases, GRU is good, and for some cases, LSTM is good. So in your tests, if you want to ever try a GRU and an LSTM, I'd recommend you try them both and see which is working best for you. Okay, the thing about GRU is it has the forget gate, but they call it the reset gate. They have the input gate, but they call it the update gate. But they don't have the output gate, because remember, output gate in the LSTM was used to create the short-term memory out of the cell memory. Well, since we have short-term and long-term memories, the cell state and the hidden state fused in this design, they didn't have the output gate. So this is an efficient design. That was their purpose, to do the same job more efficiently with less computation. Okay, no hidden state. Then these slides are discussing the things that I've already told you. GRU do not have an output gate. GRU's single cell hidden state with vector is state is vectoral. It's just fused in it. How does it compare to LSTM in practice? LSTM is more transparent because you have long short-term memories separate, but GRU is more efficient. It has less number of computations. In practice, they perform similar. Their comparison detailed subject, just like a brief summary of what I just told you. And actually, Bengio did a study on that, empirical evaluation of gated recurrent neural networks on sequence modeling. They have this discussion for other variants as well. And there are some links and there are some blogs discussing that discussion. So I strongly recommend you go over these if you're going to use a LSTM or GRU if you're doing sequence modeling, to select which one to use. Okay, so I guess it is enough for the first part. So I'm going to give another break right now, and 15 minutes from now, so at 5 to 11, we're going to meet here, and we're going to talk about an introduction to NLP. Any questions? Let me ask first.